Venus has destroyed more spacecraft than any other world we have ever tried to reach. Every single probe that descended into its atmosphere was either crushed, cooked, or consumed, usually within minutes. And for a long time, we had no idea why. Because from the outside, Venus looks like the easiest target in the solar system, closer to Earth than Mars, similar in size, wrapped in bright, reflective clouds that made it shine like a lantern in the night sky. So we sent machine after machine toward it, and all went silent. This is the story of what Venus is actually doing to them, and why, even now, no spacecraft has survived its surface for more than 2 hours. When scientists first began turning their telescopes toward it in the early days of the space age, many of them genuinely believed it might be habitable. The thick clouds could mean moisture. The closeness to the sun could mean warmth. A warm, wet world with dense cloud cover sounded, at the time, like a reasonable description of early Earth. They were wrong. But the way they discovered they were wrong, that is the story worth telling. Venus sits at a distance of roughly 0.72 AU from the Sun. At its closest approach to Earth, it is nearer to us than Mars ever gets. It is twice as close, in fact. And because of that proximity, it was one of the first targets chosen when the space age began. If humanity was going to practice sending machines to other worlds, Venus was the obvious first rehearsal. The Soviet Union committed to that rehearsal more than anyone. Between 1961 and 1984, they launched more than 24 missions toward Venus. Some of them never left Earth orbit, their rockets misfired, their stages cut short, their trajectories calculated wrong. Some made it to interplanetary space and then went silent, drifting past Venus without returning a signal. Some arrived and were immediately destroyed before they could transmit a single byte of data. But some of them succeeded, and what they returned in those brief, violent minutes of survival changed everything we thought we knew about our nearest neighbor. Now, before we get to what they found, we need to understand the context in which they were being sent, because this was not purely a scientific program. This was the Cold War conducting science by other means. The Americans and Soviets had divided the inner solar system between them, not formally, not by treaty, but by the logic of parallel ambition. The Americans pointed their programs toward the Moon and Mars. The Soviets pointed theirs toward Venus. Those were the unspoken boundaries. And within those boundaries, every mission carried a weight that had nothing to do with atmospheric chemistry or orbital mechanics. Every mission carried national pride. The engineers behind the Venera program, the Soviet name for their Venus missions, operated in a culture of enforced secrecy unlike anything in the Western space programs. Success was announced with fanfare. Failure was classified. In practice, this meant that the engineers knew things the public did not. They had access to the full record of what had been attempted and what had been destroyed. They could see the pattern. They just could not say it out loud. That pattern, mission after mission, disappearing into a planet that offered no second chances, is what makes the Venus program one of the most quietly extraordinary chapters in the history of exploration. Not because of the glory, because of the persistence. Because they kept redesigning and relaunching into a place that had never once given them anything easily. The first attempt to reach Venus happened on February 4th, 1961. It is listed in the mission archives as Sputnik 7. The rocket's final stage failed. The spacecraft never escaped Earth's gravity. It re-entered the atmosphere and was gone within days. There was no announcement. 8 days later, the Soviets tried again. Venera 1 made it to interplanetary space, a genuine achievement in 1961. And then, 7 days into the journey, contact was lost. The spacecraft continued toward Venus on its calculated trajectory, silent and unreachable, and flew past the planet without returning a single measurement. It was close enough that, under other circumstances, it could have changed everything. Instead, it just disappeared. The Americans launched Mariner 1 toward Venus on July 22, 1962. It veered off course almost immediately after launch. Ground controllers destroyed it within 5 minutes. They launched Mariner 2 5 weeks later. This time it worked. On December 14, 1962, Mariner 2 became the first spacecraft in history to conduct a successful scientific flyby of another planet. It passed within roughly 35,000 kilometers of Venus and swept the planet with its instruments. What it found was the first data point that should have warned everyone. The surface temperature of Venus was around 428 degrees Celsius, maybe higher. The instruments were not precise enough to be certain, but the number was unmistakable. This was not a warm, wet world. This was a furnace. Now here is the strange part. And this is the single most important anomaly in the entire story of Venus exploration, so it is worth stopping here for a moment. Venus is farther from the Sun than Mercury. It receives less solar energy per square meter than Mercury does, and yet its surface is significantly hotter. The average surface temperature of Venus is around 740 Kelvin, roughly 467 degrees Celsius. Mercury's average temperature on its hot side is around 430 degrees. Venus is hotter. A planet that is further from its star, receiving less of its energy, is somehow running at a higher temperature than the planet closest to the Sun. That fact, that single, counterintuitive data point, is the key to understanding why every spacecraft sent to Venus was destroyed, because the temperature is not an accident. It is not a geological quirk. It is the result of an atmospheric process so extreme, so self-reinforcing, that it has transformed an Earth-sized planet into something that bears almost no resemblance to what you would expect from the outside. So, what is Venus actually made of, at the atmospheric level, and why does its atmosphere produce conditions that destroy metal within minutes? That is where the story gets genuinely strange. The atmosphere of Venus is composed of 96.5% carbon dioxide. Almost everything else is nitrogen, with trace amounts of sulfur dioxide, water vapor, carbon monoxide, and a handful of other compounds in quantities almost too small to measure. By itself, that composition sounds manageable. Carbon dioxide is not exotic. We produce it here on Earth every time we breathe. The problem is not what Venus's atmosphere is made of. The problem is how much of it there is, what it does to heat, and what its cloud layer is made of. Let's start from the top and work our way down. At 100 kilometers above the surface, Venus's upper atmosphere is relatively calm, thin, cold. As you descend towards 65 kilometers, you enter the cloud deck. From the outside, these clouds look clean and white, almost inviting. The images returned by spacecraft show swirling, layered formations that look something like terrestrial weather systems viewed from above. They are not made of water. The clouds of Venus are composed primarily of sulfuric acid, concentrated sulfuric acid, at densities of between 75 and 95% by mass. This is not the diluted sulfuric acid used in car batteries. This is near pure sulfuric acid in droplet form, suspended in the atmosphere, swirling in cloud formations that span the entire planet. They extend from roughly 45 kilometers, altitude up to 70 kilometers. They are global. They are permanent. They do not clear. They do not have gaps. The surface of Venus has not seen direct sunlight in any meaningful sense for billions of years. These sulfuric acid clouds are produced continuously by a photochemical reaction in the upper atmosphere. Ultraviolet light from the sun breaks down carbon dioxide and reacts with sulfur dioxide and water vapor. The products of that reaction combine to form sulfuric acid, which condenses into droplets and falls into the cloud layer. It is a self-sustaining chemical factory running on solar energy, producing acid in industrial quantities every second of every day. The clouds are also extraordinarily reflective. Venus reflects approximately 75% of the sunlight that falls on it, more than any other planet in the solar system. This is why it appears so bright from Earth. And here is the cruel irony. Because so much sunlight is reflected back into space before it even reaches the surface, Venus actually receives less solar energy at ground level than Earth does. The surface of Venus is somewhat dim, but the surface temperature is almost 500 degrees Celsius. The heat is not coming from the sunlight reaching the surface. The heat is trapped. This is the greenhouse effect, not in the moderate form that climate scientists discuss on Earth, but in its most extreme possible expression. Sunlight enters through the cloud layer in limited quantities. The surface absorbs it and re-radiates it as infrared radiation. The dense carbon dioxide atmosphere prevents that infrared radiation from escaping back into space. The heat accumulates. Over billions of years, it has accumulated to the point where the surface temperature is stable at roughly 462 degrees Celsius day and night, poles and equator, with almost no variation. The temperature on Venus is so stable, in fact, that the difference between the hottest and coldest points on the surface is only a few degrees. The planet is thermally locked. There are no seasons. There is no day-night temperature cycle in any meaningful sense. The slow retrograde rotation of Venus, it takes 243 Earth days to complete one rotation, means that a single Venusian solar day lasts about 117 Earth days. And yet the surface temperature barely changes across that entire period. The atmosphere stores and redistributes heat so efficiently that the entire planet runs at roughly the same temperature at all times. Now, the pressure. The atmospheric pressure at the surface of Venus is approximately 92 times the atmospheric pressure at sea level on Earth. To put that in physical terms, it is equivalent to the pressure you would experience at a depth of 900 meters beneath the surface of the ocean. If you were somehow transported to the surface of Venus without protection, you would not have time to be burned. The pressure would crush you first. That pressure is produced by the sheer mass of the atmosphere above. The total mass of Venus's atmosphere is about 93 times the total mass of Earth's atmosphere, despite the fact that Venus is only slightly smaller than Earth. The planet has retained an enormous quantity of gas, and that gas bears down on the surface with a force that destroys standard engineering materials the way deep ocean pressure destroys submarines that dive too far. At the surface, under those conditions, carbon dioxide technically stops being a gas in the conventional sense. At 92 atmospheres of pressure and 462 degrees Celsius, carbon dioxide becomes what physicists call a supercritical fluid, a state of matter that has the density of a liquid but the flow characteristics of a gas. The lowest layer of Venus's atmosphere is, in a precise technical sense, a shallow ocean of supercritical carbon dioxide, a sea of hot, dense, chemically active fluid covering the entire planet. And the winds near the surface, while slow by the standards of the upper atmosphere, carry devastating kinetic force because of that density. Surface wind speeds on Venus are generally less than 2 meters per second. On Earth, that would be a barely perceptible breeze. On Venus, because the atmosphere at the surface is 65 kilograms per cubic meter, roughly 6.5%, the density of liquid water, even a slow wind, exerts forces comparable to a moderate ocean current. It moves material. It erodes rock. It could topple structures that would stand easily on Earth in a calm wind. High in the atmosphere, the situation is entirely different. At the cloud tops, around 60 to 70 kilometers, altitude winds blow at roughly 100 meters per second. That is 360 kilometers per hour. The entire Venusian atmosphere at that level rotates around the planet in just 4 Earth days, even though the planet itself takes 243 days to complete a single rotation. The atmosphere moves 60 times faster than the world beneath it. This phenomenon, called atmospheric superrotation, is one of the genuinely unresolved mysteries of planetary science. We observe it. We can describe it. We still do not fully understand what drives it. So here is the summary of what any spacecraft entering Venus must survive. In the upper atmosphere, Nothing extreme. In the cloud layer between 45 and 70 kilometers, concentrated sulfuric acid capable of corroding most known materials. Below the clouds, temperatures rising past the operating range of standard electronics, accelerating toward 500 degrees. At the surface, pressures equivalent to deep ocean, temperatures that melt lead, and an atmosphere so dense it behaves more like a fluid than a gas. Every one of those conditions is lethal to spacecraft in its own way. Together, they are why the surface of Venus has not been visited by any spacecraft in over 40 years. But there is one more detail worth noting before we move on. A detail that will become important later. At approximately 50 to 65 kilometers above the surface of Venus, there is a narrow band of the atmosphere where the temperature drops to somewhere between 0 and 50 degrees Celsius, and the pressure is close to Earth's surface pressure. In that specific altitude range inside clouds made of sulfuric acid, in an atmosphere made of carbon dioxide, in a planet with no magnetic field and no liquid water on its surface, the temperature and pressure are, by those two measurements alone, the most Earth-like environment in the solar system, outside of Earth itself. We will come back to this. When Venera 4 arrived at Venus on June 12, 1967, it became the first spacecraft to return scientific data directly from inside another planet's atmosphere. The probe entered the atmosphere and deployed a parachute. It began descending. It transmitted data continuously: temperature, pressure, atmospheric composition. The readings confirmed what Mariner 2 had hinted at. Carbon dioxide dominated. Temperatures were climbing fast. Pressure was mounting. The preliminary analysis suggested the probe had transmitted all the way to the surface. That turned out to be wrong. Later reconstruction of the data revealed that Venera 4 had been crushed by the atmosphere at an altitude of roughly 25 kilometers. It never reached the ground. The probe had been designed to withstand 25 atmospheres of pressure. The atmosphere of Venus exceeded that before the spacecraft was even halfway down. The engineers went back to their calculations. They had underestimated the planet. The atmosphere was denser than any of their models had predicted. The probes needed to be stronger. The pressure vessels needed thicker walls. The design envelope needed to be rebuilt around a planet that was far more hostile than the instruments of the early 1960s had been capable of measuring. Venera 5 and 6 arrived in May 1969, within a day of each other. Both deployed parachutes. Both transmitted atmospheric data for roughly 50 minutes as they descended. Both were crushed before reaching the surface. But each one descended further than Venera 4 before the atmosphere won. The engineers were learning in the only way Venus would allow them to learn, which was by losing machines one at a time. Venera 7, arriving in August 1970, was designed differently. The engineers had made the parachute smaller, deliberately not to slow the descent, but to accelerate it. They had calculated that the probe's best chance of returning surface data was to get through the most dangerous altitude range as fast as possible. Less time in the crushing mid-atmosphere meant a better chance of arriving at the surface with instruments still functioning. It worked. Venera 7 touched down on the surface of Venus. Its parachute may have been damaged by high winds during descent. It arrived faster than planned, possibly because the chute partially failed. It transmitted a weak signal from the surface for 23 minutes. Temperature, 475 degrees Celsius. Pressure, approximately 90 atmospheres. And then, silence. 23 minutes. That was the entire window in which humanity received its first data from the surface of another planet. Venera 8 followed in 1972 and survived for 50 minutes on the surface, more than twice as long. It measured light levels and found them higher than expected. The surface of Venus, despite being buried under kilometers of opaque cloud, received enough diffuse light that photography would be possible. The engineers filed that away. Venera 9 and 10 arrived in October 1975, and each separated into two components: an orbiter that would remain in space and a lander that would descend. The landers were the most capable probes yet sent to Venus. They carried cameras. They carried soil analysis instruments. They carried atmospheric sensors optimized for the surface environment. The Venera 9 lander touched down and became the first spacecraft to transmit a photograph from the surface of another planet. Not Mars, not the Moon, Venus. The image showed angular slabs of rock, recently fractured, with sharp edges that had not yet been worn smooth. This told geologists something immediately. The surface of Venus was geologically young. Old rocks erode. These had not. Venus was still active. Venera 10 landed 2 days later, 2,000 kilometers away. Its image showed a different terrain entirely flatter, with older-looking rock formations and a more eroded surface. 2 landing sites, 2 completely different geological stories. Venus was not uniform, it was complex. Both landers survived for roughly an hour before their instruments failed. The heat, the pressure, and the chemical environment had worked their way through the thermal insulation and into the electronics. The probes went silent on schedule not because anything unexpected had happened, but because the engineers had calculated almost exactly how long they would last, and they had been right. Then came Venera 11 and 12 in December 1978. Both landers reached the surface. Both survived. Both failed in a different way. The lens caps on both cameras did not separate. The cameras were physically present, mechanically functional, thermally protected, and completely blind from the moment of landing. The soil analyzers also failed on both probes. The missions returned atmospheric data and detected signals interpreted as possible evidence of lightning in the clouds, but the surface images, the photographs of what Venus actually looked like up close, did not come. The engineers solved the lens cap problem. Venera 13 arrived in March 1982 and became the most successful Venus surface mission in history. The lander touched down, the lens caps separated correctly, and the cameras functioned. It transmitted the first color photographs from the surface of Venus. The images showed an orange-tinted landscape. The color was an artifact of the thick atmosphere filtering the light with flat bedrock covered by thin layers of loose material and thin, angular rocks scattered across it. It looked, in a certain light, almost volcanic. Venera 13 survived for 127 minutes. 2 hours and 7 minutes on a surface where the temperature is almost 500 degrees and the pressure is 92 atmospheres. That record has never been broken. No lander has ever survived longer on Venus. It remains the longest surface operation of any spacecraft on any planetary surface except Earth's Moon and Mars. Venera 14, arriving a few days later, lasted 57 minutes. Its soil analyzer sampled the surface and found basaltic rock composition similar in broad terms to basaltic volcanic rock on Earth. Venus, at least at those 2 landing sites, had a surface that geologists recognized. After the Vega missions in 1985, which delivered landers and balloons to Venus en route to Comet Halley, the Soviet lander program ended. The Soviet Union was moving toward collapse. Funding contracted. The planetary science program that had pioneered Venus exploration quietly stopped launching. The last spacecraft to land on Venus did so in 1985. The surface has not been visited since. To understand what Venus does to spacecraft, it helps to compare what other worlds do and do not do. Mars has a thin atmosphere, less than 1% of Earth's surface pressure. Landers there face cold temperatures, radiation exposure, and dust storms, but the mechanical and thermal stresses are within the range that standard engineering can address. Mars rovers have operated for years, decades in some cases. The Opportunity rover, designed for a 90-day mission, operated for nearly 15 years. The Curiosity rover, which landed in 2012, is still operational as of 2026. The surface of Mars is hostile by Earth standards. By Venus standards, it is almost comfortable. The Moon has no atmosphere at all. Landers there face extreme temperature swings between lunar day and night, and exposure to cosmic radiation, but no pressure, no chemical corrosion, no wind. The descent stages from the Apollo lunar modules are still sitting exactly where they landed more than 50 years ago, exposed to vacuum and temperature extremes, but structurally intact. Nothing on the Moon attacks them. Venus would have consumed them within the hour. Jupiter's atmosphere destroys probes with pressure as you descend into it, much like Venus, but the timeline is different. The Galileo atmospheric probe, dropped into Jupiter in 1995, survived for about an hour before the pressure and temperature destroyed it at a depth where the atmospheric pressure was around 23 atmospheres. On Venus, 23 atmospheres is reached at an altitude of roughly 25 kilometers above the surface. A probe designed to survive Jupiter's atmosphere would still be destroyed before reaching the Venusian surface. Venus gives you the worst of multiple planetary environments simultaneously, and it gives them to you all at once from the moment of atmospheric entry. There is no gradual adjustment. There is no relatively safe staging zone where a spacecraft can establish itself and begin operating before conditions worsen. The sulfuric acid clouds begin at 45 kilometers. The temperature has already climbed past 100 degrees before you clear them. By the time you reach the surface, every system on a standard spacecraft has either failed or is on the verge of failure. The electronics problem is particularly unforgiving. Standard silicon-based transistors, the foundation of essentially all modern computing, begin to degrade at temperatures above about 150 degrees Celsius. They do not malfunction in recoverable ways. They simply stop conducting electricity correctly. The circuits that form a spacecraft's brain stop working. At Venus's surface temperature of 462 degrees, conventional electronics do not last minutes, they last seconds. The Soviet Venera probes got around this through an approach that was essentially thermal brute force. They built their electronics packages inside heavily insulated pressure vessels, and they used phase-change heat-sink materials, substances that absorb large amounts of heat as they transition from solid to liquid, similar to the way ice absorbs heat as it melts. This buffered the internal temperature of the spacecraft long enough for its instruments to function, but the buffer was finite. The heat always penetrated eventually. The phase-change materials completed their transition and stopped absorbing. The temperature inside the spacecraft climbed. The electronics failed. Engineers have identified only 2 realistic paths to long-duration surface operations on Venus. The first involves nuclear-powered refrigeration, a cooling system powerful enough to maintain survivable temperatures inside a spacecraft despite the external heat. The power requirements for such a system are enormous, and the mass penalty is severe. No mission has yet been built around this approach. The second path involves developing entirely new categories of electronics components made from wide bandgap semiconductors like silicon carbide or gallium nitride, which can operate at temperatures of 500 degrees Celsius or higher. Basic versions of these components have been demonstrated in laboratory settings. None have been deployed in a surface mission to Venus. Both solutions exist in principle. Neither exists in practice, in a form that has landed on Venus. This brings us to Cosmos 482. On March 31st, 1972, 4 days after the successful launch of Venera 8, the Soviet Union launched what was almost certainly an identical twin probe on the same mission profile. An incorrectly set timer caused the Block L upper stage to cut off prematurely. The spacecraft failed to reach escape velocity. Instead of departing on a trajectory toward Venus, it was left in an elliptical Earth orbit, its apogee reaching nearly 10,000 kilometers. The Soviets designated it Cosmos 482 and said nothing further about its intended purpose. The spacecraft separated into pieces. Most of them re-entered Earth's atmosphere within days. But the descent craft, the Venera-class lander, the titanium-shelled pressure vessel built to withstand the surface of Venus, remained in orbit. It drifted in its elliptical path for decades. Its orbit slowly decayed. Year by year, the perigee dropped a little lower. and the drag of Earth's upper atmosphere bled off a little more velocity. On May 10, 2025, it finally came down. According to Roscosmos, the lander impacted the northeastern Indian Ocean at 6:24 in the morning UTC, west of Jakarta. The European Space Agency, tracking the object from Germany, lost radar contact between the 6 o'clock pass and the 7:30 pass, and concluded that re-entry had occurred in that window. Whether the lander survived re-entry to reach the ocean in one piece is not known with certainty. It had been designed to withstand 300 times the force of gravity and 100 atmospheres of pressure. Its heat shield, intended for Venus, was likely more than sufficient for Earth's relatively gentle atmospheric entry. But the parachute system had spent 53 years in space. The fabric, the deployment mechanisms, the pyrotechnic release systems, all of them would have degraded significantly over that period. Without a functioning parachute, the terminal velocity would have been much higher than intended. The European Union's space surveillance and tracking network concluded that it most likely survived and reached the ground or ocean largely intact. A spacecraft built to land on Venus, spending 53 years in orbit around Earth, ultimately re-entering as an uncontrolled piece of space debris. That is perhaps the strangest footnote in the entire story of Venus exploration, and it tells you something important about the engineers who built it. They were not cutting corners, they built things to last. Now we return to that altitude band, 50 to 65 kilometers above the surface of Venus. The conditions there are, by temperature and pressure, the most Earth-like environment in the solar system outside of Earth itself. More Earth-like, on those two measures, than the surface of Mars. The clouds are made of sulfuric acid. The air is carbon dioxide. There is very little available water. These are serious barriers to life as we understand it. But the temperature 0 to 50 degrees Celsius and the pressure close to 1 Earth atmosphere fall within the range that life on Earth routinely occupies. This has been known since the early days of Venus exploration, and it has generated a persistent, unresolved question that the data neither confirms nor rules out. In September 2020, a team of astronomers using two of the world's most powerful radio telescopes reported what appeared to be the detection of phosphine in Venus's upper cloud layer. Phosphine is a molecule composed of one phosphorus atom bonded to 3 hydrogen atoms. On Earth, phosphine is associated with anaerobic microbial ecosystems and the digestive systems of animals. No known abiotic chemical process on Venus should produce it in the quantities the team reported. It is what scientists call a potential biosignature, a chemical signal that could, under the right circumstances, indicate the presence of life. The announcement was made carefully. The researchers did not claim they had found life. They said they had detected a compound they could not explain by known chemistry, and they were inviting the scientific community to try to explain it. The scientific community responded immediately and with considerable skepticism. An interpolation error was found in the original data processing, a flaw in the algorithm used to analyze the spectroscopic signal. When the data was reprocessed with the corrected algorithm, the apparent phosphine signal dropped dramatically. Some subsequent analyses found no detection at all, setting upper limits of less than 1 part per billion. Others found a reduced signal consistent with roughly 1 part per billion. In September 2024, preliminary analysis of new telescope data suggested a phosphine concentration of around 300 parts per billion at 55 kilometers altitude. That data is still being processed and verified. The debate is unresolved. The phosphine may be real. It may be an artifact. The instruments capable of definitively answering the question have not yet been pointed at Venus with sufficient precision or sent into Venus's atmosphere to measure directly. But the phosphine question is not the only strange thing about those clouds. It is not even the oldest strange thing. Since the first ultraviolet photographs of Venus were taken, astronomers have observed dark patches in the cloud layer. These patches absorb ultraviolet radiation in ways that no known chemical compound present in the Venusian atmosphere fully accounts for. They affect the weather patterns of the planet. They appear at certain altitudes, in certain latitudes, in patterns that shift and evolve over time. Scientists call them the unknown UV absorber. In 1963, Carl Sagan published a paper suggesting that microorganisms in the upper atmosphere might be the agent responsible for the UV absorption. He was not claiming life existed there. He was noting that the observation was consistent with that possibility. That paper was written over 60 years ago. The unknown UV absorber is still unknown. In 2026, a team of researchers from Arizona State University, the Johns Hopkins Applied Physics Laboratory, and Sandia National Laboratories presented a study that approached the question of life in Venus's clouds from an entirely different direction. Not whether life could evolve there, but whether life from somewhere else might have arrived. The idea is called panspermia. It is the hypothesis that life, or the chemical building blocks of life, can travel between planetary bodies on rocks ejected by major impact events. When a large asteroid or comet strikes a planet, it can blast surface material into space at velocities high enough to escape that planet's gravity. Some of that material can, over timescales of thousands to millions of years, reach another planet. Martian meteorites have been found on Earth. Earth rocks have almost certainly reached Mars. The transfer is real. Whether any living organisms have ever survived it is the open question. The researchers focused specifically on whether Earth rocks could deliver living microorganisms to the clouds of Venus. Not to the surface is inimical to any life we know of, but to that specific altitude band where the temperature and pressure are Earth-like. They used a physics model called the pancake model, which describes how a rock called a bolide behaves as it enters a planetary atmosphere. The model tracks the bolide's descent, its deceleration, the forces tearing at its surface, and the point at which it either fragments gradually or explodes in what is called an airburst. Their calculations found the following. A typical meter-scale rock entering Venus's atmosphere at around 25 kilometers per second would fragment and airburst at approximately 82 kilometers above the surface, well above the cloud. Tops. At that point, roughly 40% of the rock's original mass would still be intact, not yet vaporized by the heat of entry. A small fraction of that surviving mass, estimated at roughly 1/10 billionth of the total, would disperse as fragments small enough to remain suspended in the cloud layer. Those fragments, measuring 25 micrometers or less in diameter, could remain lofted in the clouds for at least several Earth days. Prior studies estimated that roughly 13% of material ejected from Earth reaches Venus over geologic time. Over the past 3.5 billion years, that corresponds to approximately 9 trillion kilograms of Earth material delivered to Venus's atmosphere, divided into something on the order of 79 million individual meter-scale bolides, each one carrying whatever microorganisms may have been living in the rock when it was ejected. The researchers' best estimate: approximately 100 cells per Earth year may be dispersed into Venus's cloud layer from Earth-origin rocks. Over the age of Venus's surface, estimated at around 240 million years or more, that could mean upward of 20 billion cells delivered in total. Every parameter in that calculation carries significant uncertainty. The fraction that disperses into cloud-lofting particle sizes was extrapolated from meteorite fall data far beyond its measured range. The fraction of cells that could survive ejection from Earth, the interplanetary journey, and atmospheric entry at Venus is genuinely unknown. The fraction that could survive in the cloud environment, in concentrated sulfuric acid with low water availability, at temperatures and pressures that are Earth-like but in a chemical context that is entirely alien, is deeply uncertain. The researchers are explicit about all of this. They are not claiming life exists in Venus's clouds. They are calculating whether the mechanism of delivery is plausible, and their conclusion is that it is. The math does not rule it out. If a future mission finds life in Venus's clouds, the possibility that it came from Earth carried there not by spacecraft, but by rocks flung into space by ancient impacts would be a serious scientific hypothesis, not a footnote. The researchers note, in the measured language of scientific papers, that their models predict life may exist in the clouds of Venus for at least a few days per century, courtesy of Earth. A few days per century, transient, uncertain, but not zero. Look at the mission table for Venus and let it sit with you for a moment. Sputnik 7, 1961 failure. Venera 1 contact lost. Mariner 1 destroyed on launch. Mariner 2 success, flyby only. Sputnik 19, 20, 21 rocket failures. Cosmos 27 failed to reach Venus. Zond 1 communications lost. Venera 2 contact lost just before closest approach. Venera 3 impacted the surface, returned no data, the first object from Earth to reach another planet, and the first one to be immediately destroyed by it. Cosmos 96 failure. Venera 4 crushed before reaching the surface. Cosmos 167 failed to escape Earth orbit. Cosmos 359 same. Cosmos 482 stranded in orbit for 53 years before falling back to Earth. And woven through those failures, the brief survivals. Venera 4 confirming the composition before being crushed. Venera 5 and 6 mapping the pressure gradient as they descended and died. Venera 7 surviving just long enough to whisper 23 minutes of surface data before going silent. Venera 8 extending that to 50 minutes. Venera 9 and 10 returning photographs. Venera 13 setting its 2-hour record and then going quiet, as every machine sent to that surface eventually must. The pattern is consistent. Venus does not allow extended stays. It grants brief windows, minutes, occasionally hours, and then it takes its machines back. The reasons are understood now. The temperature beyond the range of standard electronics, the pressure beyond the range of standard structures, the chemistry of the clouds corroding anything that passes through them, the supercritical carbon dioxide at the surface, behaving more like a hot, dense ocean than an atmosphere. These are not mysteries anymore. We know why Venus destroys spacecraft. We understand it in detail. What we do not have is a material solution, a way to build something that can survive there long enough to do meaningful science. Missions are being planned. NASA's Davinci mission, selected in 2021, will send an atmospheric probe to Venus to measure the composition of the lower atmosphere and determine whether the planet ever had surface oceans. It will descend through the clouds and survive the environment for as long as its thermal design allows. NASA's Veritas mission, currently targeting no earlier than 2031, will map the surface using radar from orbit. The European Space Agency's Envision orbiter is targeting a launch in the early 2030s and will study the planet from its inner core to its upper atmosphere. India has proposed a Venus orbiter called Shukrayaan for 2028. None of these are landers. None of them will descend to the surface. The surface remains, for now, beyond the reach of anything we know how to build and keep alive. And so, we orbit. We probe the clouds from above and below. We measure the composition of the atmosphere at altitude. We look for the unknown UV absorber and argue about whether the phosphine signal is real. We calculate the rate at which Earth rocks might be delivering microorganisms to the acid clouds of our nearest neighbor. We build increasingly sophisticated models of a surface we cannot visit and a geological history we cannot directly sample. Venus is not cooperating. It never has. What we know, after 6 decades of missions and dozens of destroyed spacecraft, is this: Venus was probably not always the way it is now. The ratio of heavy to light hydrogen in its atmosphere suggests it may once have had liquid water on its surface, possibly for as long as 2 billion years. Something happened. The climate shifted. A runaway greenhouse effect accelerated. The water evaporated. The carbon dioxide accumulated. The surface heated. And in that transition, which may have taken hundreds of millions of years, whatever may once have been possible on Venus became permanently, irreversibly impossible on the surface. What it left behind, in that narrow band 50 kilometers up, is a layer of clouds that absorbs ultraviolet light in ways we cannot fully explain, that may or may not contain a molecule with no known abiotic origin, and that researchers now calculate might receive a quiet, steady trickle of Earth life delivered by interplanetary rocks, perhaps 100 cells per year, drifting in the acid, surviving for a few days before the environment claims them too. The same planet that destroys our machines may, in some technical sense, be receiving our biology. There is something in that worth sitting with. We build spacecraft to reach Venus, and it destroys them. We lose contact. We rebuild. We lose contact again. We watch landers survive for minutes and hours and record those minutes and hours as victories. And while we are doing all of that, while we are engineering and calculating and failing and trying again, the planet may already have something of us in it, carried there long before any of our probes, on rocks that left Earth without anyone's permission and arrived without anyone watching. We have never confirmed life anywhere but here. We do not know whether the clouds of Venus contain anything alive. We do not know what the unknown UV absorber is. We do not know whether the phosphine signal is real. We do not know whether the brief window of habitability that Venus may have had in its early history was long enough, or warm enough, or wet enough for life to have ever taken hold. What we know is that we keep trying to find out, and that Venus keeps making it as difficult as any place in the solar system can. We built the machines. We aimed them at the brightest object in the night sky. We listened to the signals as long as they lasted. And every time the signal stopped, every time Venus took another one, we went back to the drawing board and started again. Because whatever is happening on that planet is still not fully explained, and unexplained things have always been where science goes next.